Hi, let us start discussing fluid mechanics, unit number 5, that is flow through pipes. Internal flows through the pipes, elbows, the T's, valves, etc., as in this oil refinery, are also found in many other industries. Okay, all chemical companies, chemical industries like pharmaceutical companies, food processing companies, and so on. So liquid or gas flow through the pipes or ducts is commonly used in heating and cooling applications, and also for fluid distribution networks. The fluid in such applications is usually forced to flow by a fan or a pump through a flow section. We pay particular attention to the friction, which is directly related to the pressure drop that might take place here, and head loss during the flow through the pipes and the ducts. The pressure drop is then used to determine the pumping power requirement. How much should be the power of a pump installed in a pipeline, or the power of maybe a fan, or it could be a blower. Now, energy losses through the pipe take place when the flowing fluid experiences many resistances, which result in the loss of energy of the fluid. These energy losses can be classified into two types rather: major losses of energy and minor losses of energy. Major losses are due to the friction, and it can be calculated using a formula, rather two formulae. One is Darcy-Weisbach equation and the second one is Kay's formula. Minor losses are the losses which occur due to presence of a different pipe fittings. Pipe fittings, for example, sudden expansion, sudden contraction, provision of a bend or elbow or a valves, and so on. So coming to the point of major energy losses, these are measured, these can be rather calculated using Darcy-Weisbach equation. Okay, consider a uniform horizontal pipe with a steady flow of a fluid, and consider a mass of a fluid between these two sections, section 1-1 and section 2-2. The flow of a fluid is a steady flow. It means the velocity is not changing with respect to time. Also, the cross-sectional area of a pipe is uniform. So diameter of a pipe is uniform. Let us consider two sections 1-1 and 2-2, and let us analyze the fluid present in these two sections. Let P1, P2 represents intensity of pressure at sections 1 and 2. Let v1 v2 represent the velocities at section 1 and 2. Okay, here 1 and 2. Say L represents the length between the two sections. Say D is the diameter, A is the cross-sectional area of pipe, and suppose HF, small h subscript F, represents loss of head due to the friction. Now let us apply Bernoulli's equation between sections 1, and 2. So we write total energy head at section 1 is equal to total head at section 2 plus loss of head due to friction, if any, between 1 and 2. So the different terms are the pressure head P1 upon gamma plus kinetic head V1 square upon 2g plus datum head Z1 at section 1 is equal to pressure head P2 upon gamma plus V2 square by 2g kinetic head plus Z2 as a datum head at section 2 plus the loss of head due to friction, that is HF. But for a given horizontal pipe, Z1 is equal to Z2, so this can be cancelled, and velocity is V1 is equal to V2. Since the diameter of pipe is same, it is uniform and it is a steady flow, so automatically it becomes a case of a uniform flow. So V1 is equal to V2. So these two terms get cancelled over here. So therefore we have P1 upon gamma, that is rho g, is equal to P2 by gamma rho g plus HF. Or you can write the frictional head loss HF equal to P1 minus P2 upon rho g. Let us call this as equation number 1. Now as the velocity of flow is constant at both of the sections 1 and 2, it means there is no acceleration of the fluid, right? There is no acceleration of the fluid, so acceleration is 0. Thus the sum of forces in the flow direction acting on the fluid mass between the two sections is 0. Now this is as per Newton's second law of motion, that is summation of F is equal to mass into acceleration, and acceleration is 0. Here acceleration is 0, so automatically summation of F is equal to 0. So all the forces acting on fluid mass are written as, there will be a pressure force at section 1, that is calculated, written as P1 intensity of pressure into area. This is towards right in the direction of flow, so positive. Then we have pressure force at section 2. This is written as P2 into corresponding area A, cross-sectional area. This will be against the flow direction, towards left, so negative sign. And we have third, a frictional force F1. This frictional force is the force offered by the surface of the pipe, and it resists the movement of the fluid which is taking place towards right. So naturally the force will be towards left, so that's why we have minus sign. So summation of these three forces is written here, P1A minus P2A minus F1 is equal to 0. And by rearranging you can get F1 is equal to P1 minus P2 into A as equation number 2. Now experimentally the frictional resistance force, so this one F1 force, experimentally this F1 is given by Froude as F1 is equal to F dash into capital A subscript W, AW into V square, where F dash means frictional resistance per unit wetted area per unit velocity. AW represents the wetted area and V represents the velocity of flow. Therefore, F1 can be written as F dash into the wetted area is nothing but perimeter into length. So perimeter is pi into d into length into V square. Thus, from equation number 2, substituting this in equation 2, we have P1 minus P2 into area is equal to F1, and that is equal to F dash into PL into V square. So we can simplify as P1 minus P2 is equal to this term on the right hand side. Thus, substituting P1 minus P2 as HF into rho g from equation number 1 towards on the left hand side. So this is equal to F dash into L into V square into perimeter pi d upon area is substituted. Area is cross sectional area. Remember, this is cross sectional area multiplying the pressure. So that goes to down as a denominator. It is pi by 4 d square. So thus HF into rho g is equal to F dash into LV square into 4 by d. Or we can write HF, the frictional head loss, is equal to F dash upon rho g into 4 LV square upon d. Here F dash upon rho is equal to F by 2, small f by 2, where small f means Darcy coefficient of friction. Okay, small f dash means frictional resistance, force per unit wetted area per unit velocity, while only small f means Darcy coefficient of friction. So f dash by rho is equal to, substituted as small f by 2. So we get a formula HF equal to 4 small f LV square upon 2 GD. 4 small f LV square upon 2 GD. Or it can be written as simply capital F LV square upon 2 GD. So these are the formulae for HF, that is frictional head loss, and this entire equation is called as Darcy-Weisbach equation, which gives you the value of frictional head loss, that is expressed in terms of meter. HF expressed in terms of meter of a fluid. Okay, here capital F is equal to 4 times small f, which is known as friction factor. Capital F is known as Darcy friction factor, and it is dimensionless term, whereas the small f is called as Darcy coefficient of friction. Okay, so there should not be any confusion in remembering this formula of a Darcy-Weisbach equation. If you are writing it HF equal to 4 FLV square upon 2 GD, then if there is a 4 here, then it means the F term is Darcy coefficient of friction. And if you are using the another formula, that is FLV square upon 2 GD, then in this one capital F means a Darcy friction factor, and there is a relation between these two. Friction factor is equal to 4 times coefficient of friction. So we have a note 1, small f, that is coefficient of friction, is a function of Reynolds number for laminar flow in the pipe. For a laminar flow in a pipe, Darcy coefficient of friction simply depends on Reynolds number. It's a function of Reynolds number, and it is expressed as small f is equal to 16 upon Reynolds number when Reynolds number is less than 2000, okay, or it may be 2300 for a laminar flow in a pipe. If there is a turbulent flow in a pipe where Reynolds number is more than 4000 and less than 10 lakhs, then coefficient of friction small f is expressed as 0.079 divided by Reynolds number raised to 1/4. Now we have the Moody's chart or a Moody's diagram. This is a chart which is made up of a certain data where we have a Reynolds number plotted along horizontal axis, and you can see this is a logarithmic scale. Then we have a Darcy friction factor, capital F. Our terminology is capital F, Darcy friction factor, along the vertical axis on the left hand side. Okay, so it increases in upward direction. And there is another term called as relative roughness. Relative roughness, that is epsilon upon capital D on the right hand side of a vertical axis. And here you can see there are number of curves which relate all these three parameters at a time. Epsilon means it is the roughness value. Here you can see in this table, here you can see these are values of roughness epsilon for different materials. Okay, different materials have different surface roughnesses. And epsilon upon capital D. Now capital D means the pipe diameter, internal diameter of the pipe. So ratio of these two is called as relative roughness. Okay. The friction factor in fully developed turbulent flow in a pipe depends on the Reynolds number as well as relative roughness epsilon upon D. While it depends only upon Reynolds number for a laminar flow in a pipe, fully developed laminar flow in a pipe. For turbulent flow, friction factor also depends on relative roughness. So we have some observations from the Moody's chart. The first one is for laminar flow, the friction factor decreases with increasing Reynolds number, and it is independent of surface roughness. So you can see here this region is a laminar flow region. So in a laminar flow region, the values of friction factor they decrease with increase in value of Reynolds number. As the Reynolds number increases, friction factor decreases. So this line is going downward. Okay. Also, the friction factor is independent of this roughness of the surface. The friction factor is a minimum for a smooth pipe, and it increases with roughness. So it is logical. Okay, for a smooth pipe, perfectly smooth pipe, the roughness epsilon can be equal to 0. This could be an ideal case. Roughness could be equal to 0, and thus the friction factor should be minimum. As the roughness increases, the friction factor value should increase. The transition region from the laminar to the turbulent regime is indicated by the shaded area in the Moody chart. At small relative roughnesses, the friction factor increases in the transition region, and it approaches the value of for smooth pipes. So transition region is this one, the shaded area over here, this one. It's a transition region between the laminar regime and the turbulent regime. So here on the right side we have turbulent regime, on the left side there is a laminar regime. Okay, and in this, as the relative roughness increases, the value of friction factor increases. This lowest curve present over here is for the smooth pipes, where epsilon upon d is equal to 0. At a very large Reynolds number, the friction factor curves corresponding to specified relative roughness curves are nearly horizontal, and thus the friction factors are independent of the Reynolds number. So this is a turbulent regime actually on the far right side, and at very high Reynolds number you can see these curves of a friction factors are almost horizontal. It means the friction factor is independent of a Reynolds number. Okay. Are independent of the Reynolds number. The flow in that region is called fully rough turbulent flow, or you can call it as fully rough flow. Why? Because as the Reynolds number increases, the thickness of the viscous sublayer decreases and it becomes so thin that it is negligibly small compared to the surface roughness height. Now coming to the discussion of minor energy losses. The loss of head or the loss of energy due to friction in a pipe, we are calling it as major loss, and the loss of energy of a fluid due to change of velocity of the fluid in magnitude and or direction caused by disturbances like the pipe fittings provided in a piping system is called as minor loss of energy. So minor loss of energy is the loss in the energy of the fluid due to the change of velocity of the fluid. Now this velocity changes either in the magnitude or in the direction or in the both sense. Now this changes in velocity takes place because of provision of a pipe fittings which are there part of a piping system. So such a loss of energy is called as minor energy losses. The loss of energy because of friction is comparatively more in case of a long pipes than due to the pipe fittings, and hence these losses are known as major loss of energy. This is the case with very long pipes. Okay, so in a very long pipes, the loss of energy because of friction is on a higher side. Magnitude wise it is on higher side as compared to loss of energy because of pipe fittings in a long pipe. While for a short pipes there could be a situation where minor losses could be comparable to the frictional losses. And there can be a situation where short pipes may have more number of pipe fittings, and that will result in higher magnitudes of a minor energy losses as compared to frictional losses. The minor loss of energy includes the following cases. Okay, the first type is the loss of head due to sudden enlargement. So here you can see there is a sudden enlargement in the diameter of the pipe from D1 to D2. So due to sudden change in diameter of pipe, what happens is flow separates from the solid boundary. Here there is a separation of a flow. Here you can see at the flowing fluid is separating from this solid boundary. Okay, and this separation results in formation of turbulent eddies due to flow separation. The fluid is not able to keep up with the surface of the pipe. Of course, eventually it is filling up the pipe and occupying the entire diameter d2, but there is a zone where flow separation has taken place, and that results in a formation of a turbulent eddies. And we know these turbulent eddies are responsible for loss of head. So this minor loss of head due to sudden enlargement or sudden expansion is given by HE is equal to V1 minus V2 bracket square upon 2G, where V1 is the velocity in a smaller pipe and V2 is the velocity in a bigger pipe. So V1 is on the upstream side, V2 is the velocity on the downstream side of the disturbance. Second one is the loss of head due to sudden contraction. This is the second type of minor energy loss. So here you can see there can be a situation where diameter of pipe suddenly contracts. Okay, so the velocity of a fluid will increase from V1 to V2. But you can see there is a formation of a vena contracta section. Okay, because there is a sharp edge over here, and that results in acceleration of a fluid, and it will slightly get separated from the pipe surface, and the fluid contracts. There is a formation of a vena contracta, and again the fluid slightly expands and fill up the pipe. So the loss of head due to contraction is actually the loss due to sudden enlargement, which is followed after vena contracta. Okay, so after vena contracta there is a sudden enlargement. So this head loss HC is given by 0.5 V2 square upon 2G, where V2 is the velocity on the downstream side. Third minor loss of head is because of at entrance of the pipe. So there can be a pipe which can be connected to a tank or a reservoir like this. So this loss occurs when the liquid enters the pipe connected to a large tank. If the corners are sharp, then the loss of energy is similar to the loss due to sudden contraction. It depends on the form of entrance of the pipe. For a sharp edge entrance, the loss is more as compared to rounded or bell mouth entrance of a pipe, and this is expressed by a formula HI is equal to 0.5 V square upon 2G, where V is the velocity in the pipe. Fourth type is loss of head at exit of pipe. The flowing fluid in a pipe has some velocity, say capital V, and it has some kinetic energy. So when the fluid exits out from the pipe, the outgoing water, which can be in the form of a free jet, has the kinetic energy in it, and which is ultimately vested. Okay, so kinetic head, velocity head in the outgoing water is V square upon 2G, and it is vested. So this loss of head at exit of pipe is written as HO is equal to V square upon 2G. Also, if the pipe is connected to a tank, then also there is a loss of the energy of the water inside the tank. The formula remains same. Fifth type of minor energy loss is the loss of head due to bend or pipe fittings. So there can be a pipe fittings like elbow over here. This is the elbow. There can be a bend. There can be a provision of a wall like this. So due to this different pipe settings, the flow separates from the boundary and formation of eddies takes place, which results in energy loss. Okay, so this loss of head in general is given as small h is equal to capital K into V square by 2G, where K represents coefficient of pipe fittings and V is the velocity of flow. Please make a note, we have not derived all these formulae for minor energy losses because these derivations are not expected as far as our syllabus is concerned. Okay, so you have to only remember the end formulae of all these minor energy losses. But of course we have a derivation for major energy loss, and that is given by Darcy-Weisbach equation. So derivation of Darcy-Weisbach equation is important. Let us see one numerical on major losses. Consider an oil of specific gravity 0.7 is flowing through a pipe of say diameter 300 mm at the rate of 500 liter per second. Find the head lost due to friction and the power required to maintain the flow of a oil for a length of 1000 meter. Take kinematic viscosity as 0.29 Stokes. So there is a pipe of 1000 meter length and it carries a oil of specific gravity 0.7. Pipe diameter is 300 mm, so 0.3 meter. Discharge rate through the pipe is 500 lps, so it is 0.5 meter cube per second. Length is 1000 meter. Kinematic viscosity is 0.29 Stokes, means cm square per second. So it is multiplied by 10 raised to minus 4, converts it to meter square per second. You have to find the head lost due to friction. So that is major energy loss, HF. And second term is power required to maintain the flow through the pipe. So major energy loss, head loss due to friction, HF, is given by Darcy-Weisbach equation. So HF is equal to 4 times small f LV square upon 2GB. So if there is a 4 as a subscript, then small f means Darcy coefficient of friction. Velocity in the pipe can be calculated as discharge per unit area of the pipe. So you plug in these values and you get a velocity as 7.07 meter per second. Let us calculate Reynolds number. Reynolds number is given by a formula RE equal to rho VD upon mu, or this is VD upon mu, where mu means kinematic viscosity. So this is equal to, plug in the values, velocity multiplied by diameter divided by kinematic viscosity. So you should get a Reynolds number equal to 7.316 into 10 raised to 4. So you can clearly see the Reynolds number is more than 4000 and something less than 10 lakhs. So it is a case of a turbulent flow in the pipe. So for a turbulent flow in the pipe, the coefficient of friction, Darcy coefficient of friction, is given by formula small f equal to 0.079 divided by Reynolds number raised to 1 by 4. So put this value of a Reynolds number and we get a value of small f, coefficient of friction, as 0.0048. Now remember, Moody's chart is used for a practical purposes, for actual designing of piping systems. And when the relative roughness values epsilon upon capital D are known to you, then only we make a use of a Moody's chart. Okay, so by knowing the Reynolds number on the horizontal axis, there is a Reynolds number, on a vertical axis there is a relative roughness values. If you know both of this, then you can get some value of a Darcy coefficient of friction on the left hand side, or rather you will get Darcy friction factor on the left hand side of vertical axis. So thus head loss due to friction, HF, can be calculated by plugging all these values. You get a value of 163.18 meter of the oil. So this much meter of the oil, this much energy in terms of head of the oil is lost in overcoming the friction, okay, which is offered by the pipe surface to the flow of the oil. Second part is power required to maintain the flow of oil in a given pipe which has a length of 1000 meter. So power required is given by a formula. Capital P is the power, that is equal to gamma cube HF. Okay, gamma means specific weight of the fluid, Newton per meter cube. Q means discharge rate, meter cube per second. So that will be Newton per second into HF. HF will be meter, unit is meter. So finally you get a unit of Newton into meter, Newton meter per second rather. This is Newton meter per second. Okay, so rho of oil can be calculated as specific gravity of oil multiplied by rho of water, 700 kg per meter cube. So this is 700 kg per meter cube into G 9.81 into Q 0.5 meter cube per second into HF 163.18 meter divided by 1000. So 1000 converts it directly into kilowatt. Otherwise you will get answer in watt. So power required is equal to 560.28 kilowatt. So this much power is required to maintain the flow of a oil at a given discharge rate, that is 500 liter per second, through the given pipe with given diameter and the given length. So this much power should be obtained from your pumping device. So we use a pump to maintain the flow of oil in a given piping system. So your pump should be able to supply this much power to that oil. That is the understanding. Power required to maintain the flow. Okay, oil will not flow on its own through the pipe, right? So there should be some pumping device. There should be some device which would work, which would supply a work to the oil or maybe to the water, and it should be capable of supplying this much water, this much kilowatt of power. So accordingly you should choose a particular pump.